9.8, we are taking a look at the wheel of algebra again. So you'll see here that I gave you the same spinner wheel that we looked at last week. I'm giving you a new copy today because the way that we labeled it is going to be all in radians rather than degrees. So we're going to be coming at this from a little different angle. We measure angles. So again, I'm trying to make algebra a little bit more exciting, so I made this prize wheel. And the same rules that we had last week are going to apply today as well. So every time the spinner must start in the position shown here above, it needs to spin in the counterclockwise direction, and if it lands on a line, the student can choose the sector on either side of that line to choose their prize. Now we're going to begin today by labeling each angle measure of these sectors in radians. And one thing that you'll notice is a tiny bit different from our unit circle is we're not going to be looking at those 45-degree angles within our spinner. And so that actually can kind of slightly change the way we think about getting our angles labeled. So we can still start with that beginning position of either being 0 radians if we do not travel at all, or 2 pi radians if we go 1 full time around the circle. And then we know that this halfway point over here on the left side is pi radians. Now, if we take a look at the whole top half of our circle, it does have equal sized sections. We don't have to do or change anything to get the pieces the same size. And we have 6 sections here. And so each one of these is literally 1/6 of pi. And so our first way to label that first position here would be pi over 6. Now, if we think about counting it by pi over 6 this time, the next position would technically be 2 pi over 6, but that simplifies to be pi over 3. From 2 pi over 6, at the top of our circle, we would have 3 pi over 6, but that simplifies to be pi over 2. 4 pi over 6 is the same thing as 2 pi over 3. And 5 pi over 6, we can't simplify that, so we just leave it as it is. If we were to keep going here, this label would be 6 pi over 6. Well, the 6's would just cancel, so it's pi. From 6 pi over 6, our next label would be 7 pi over 6. Then down here, we would have 8 pi over 6, well that's really 4 pi over 3. At the very bottom here, 9 pi over 6 is really 3 pi over 2. 10 pi over 6 is 5 pi over 3. And the very last label here, 11 pi over 6, we can't simplify it, so we just leave it as it is. If we were to keep going, 12 pi over 6 is the same as 2 pi. Now, just as we saw with our spinner last week, you can go around this circle more than one time. In fact, it was very common that when we actually spun the paperclip around, it didn't usually stop before going 1 full time. Usually, it continues spinning a little bit further. And so, if we were to think about how these labels might look if we keep going, from 11 pi over 6, we get 12 pi over 6. We could keep going here. So this next position could be 13 pi over 6. 14 pi over 6. Now that's one that we could simplify down. 15 pi over 6. We could also simplify that one. 16 pi over 6. And so on. And we could actually continue counting up by pi over 6 as many times as we would like. So that's a little something I want you to be aware of in answering our questions today. The other thing is that we could have negative angles in radians, just like we did with degrees. So if we had somebody that didn't follow the rules and went backward, an example here, if we went backward and stopped at this very first line, that would be negative pi over 6. Because if pi over 6 is the distance that we traveled, the negative sign means that's the direction that we went. And I'm just going to go ahead and leave my spinner here displayed as we start to take a look at this first question. So it says that our student Mahila really wants to win extra homework. Why does she want to win extra homework? I'm not sure. But that's the prize that she's hoping for. And so we want to try to figure out what is the smallest number of radians that she can spin in order to win. So if we're starting in our starting position here, this would be where our spinner starts. So if we go ahead and see where the extra homework is labeled, we know that she could land like anywhere within that sector, but she could also land on the line. So we want to try to focus on the line right before the extra homework label, and that's going to get us the smallest number of radians. So moving around in this counterclockwise direction to get a positive angle measure, we see that it would be 5 pi over 3 radians. Now it says in part 2 that Mahila really spun 11 pi over 3. And we want to know if she actually got that extra homework. And so 11 pi over 3 is going to represent an angle that's bigger than 2 pi. It's bigger than 1 full time around the circle, which was aligned with naturally what seemed to happen more often than not with our paperclip is it didn't usually stop so close to like less than 1 time around. A lot of times that paperclip was spinning maybe more than 1 time. And so if we were to think about these angles that I have labeled here in green, so if we're to kind of keep counting upward, we want to keep going until we can find 11 pi over 3. And I'm going to continue thinking about counting up by pi over 6. Now some of these could definitely be simplified. I'm not going to simplify them all along the way here. But I'm going to keep on going until I get something that could simplify down to 11 pi over 3. And that is happening right here at this 22 pi over 6, because when you divide the top and bottom by 2, sure enough, it turns into 11 pi over 3. And because it's in the same position, it shares a terminal side with 5 pi over 3, then yes, she does win the extra homework if she spins 11 pi over 3. The difference here in our picture is that we're going to show that she has gone more than 1 full time around. So it looks more like a big spiral arrow, like a really big spiral here, just like that. More than 1 time on that second trip around the circle is when she stops at 11 pi over 3. So what we're witnessing here is something that we saw and talked about already last week. It's a way to look at 2 different angle names that have the same terminal side of the angle. What would we call these 2 types of angles together? And 2 different ways to label the same spot. Remember, these are coterminal angles. And we looked at them last week with degrees. Here we're just labeling them in radians. Now, because we're with radians, there's going to be a slightly different process for finding the coterminal angle measure. So I'm going to ask you 2 questions here. Let me move this down so we can see our full circle. If I were to start here in the starting position, and if I were to go 1 full time around the circle, how many radians is that? 12 pi over 6, but let's simplify it down. How many radians is 1 full time around?
24. 12.
2 pi. 2 pi. Are we okay with that? All right, so it's like 1 full time around in degrees is 360 degrees. In radians, 1 full time around is 2 pi. Well, what if we changed our starting position? What if we changed our starting position to be here at 5 pi over 3? And we go 1 full time around the circle and we land in the same place? How many radians did we go? How many radians is it if you go 1 time around the circle, no matter where you start? 2 pi. And so the way we get coterminal angles in radians is we add or subtract 2 pi. That's equivalent to 360 degrees in the world of radians. So let me go back number 2, what we're noticing here is we have co-terminal angles, and the way we're going to find them in radians is we're either going to add or subtract 2 pi. It's kind of like adding or subtracting 360 degrees. And so we saw this in the picture, why 5 pi over 3 and 11 pi over 3 are coterminal. But I wanted to take a look here at the math behind it. So what's happening behind the scenes? What do we actually do if we're trying to add or subtract 2 pi? So there's 2 ways that we can look at this. So if we start with 5 pi over 3, let's start with the option of just adding 2 pi. That's going to get us a coterminal angle here that's bigger than 5 pi over 3. Well, if we're wanting to add 2 pi onto a fraction, there's a couple of things we need to do here before we can actually add. We have to turn 2 pi into a fraction, so that's going to be the first step, is to think about turning it into 2 pi over 1. But the other thing that has to happen in order to add fractions is that our denominators have to be the same. And so we're going to make an adjustment with this 2 pi over 1 fraction. We're going to multiply the top and bottom by whatever number we need to get the denominator the same as whatever the fraction is to begin with. In this case, 3. And so we're going to change the problem here. It turns into 5 pi over 3 plus 6 pi over 3. So notice here that 6 pi over 3, it's the same thing as 2 pi, it's just in a different form. Now, when we have our denominators the same, the way that we add fractions is we're just going to add across the numerators, we're going to add across the top, and keep our denominator the same. And that's how we get the coterminal angle of 11 pi over 3 just by doing a calculation. Now, we could have also gone the opposite direction. If you started with 11 pi over 3, you could subtract 2 pi, which is really 6 pi over 3 in this case. Subtract across the numerators, keep your denominator the same, and you're going to end up back at 5 pi over 3. So the version of 2 pi that you're using is always going to change based on what this first denominator is. So it doesn't always have to be 6 pi over 3. If your first denominator was 4, you could turn it into 8 pi over 4. That's another form of 2 pi. All right, so that's how we're going to deal with coterminal angles. All right, the last question here, number 3, it says here that when Macy went, the angle she made had a sine ratio of sine of theta equals -1/2. And we want to figure out what angles could she have spun. And we're going to give our answer here in radians. Veronica, would you share out what angle answers did you get here?
11 pi over 6 and 7 pi over 6.
That's great. And tell us about that. How did you get to those answers?
With the cosine and the sine of the x and the y on the surface.
All right, this is one where we want to have our unit circle here in front of us. I'm going to go ahead and just kind of sketch where those 2 angles would be. So 7 pi over 6 and 11 pi over 6. On our circle, they're the closest angles to the x-axis that are below the x-axis. And it's going to come down to the labels here, the x and y coordinates. So at 7 pi over 6, if we just copy this directly from our unit circle, those are the values we get for x and y. And then these are the values we have over here at 11 pi over 6. So because it's asking for the sine of an angle, well, we know that on our unit circle, sine is always equal to the y value. So what the question is really asking is, what's a unit circle angle that has a y value of -1/2? So I'm just going to make a little note here. This is a connection to something that we did last week, that the sine of a unit circle angle is going to require us to look at the y value of the coordinates at that angle. All right, and when you're ready, go ahead and turn your paper over to the back. All right, so we had 2 learning targets for today. So the first one was to find coterminal angles for angles measured in radians. And we saw the process that we need to do is either add or subtract 2 pi from whatever the original angle was that we're starting with. And we saw that in the calculation, we need to write 2 pi as a fraction with the same denominator. As whatever we were starting with. So for example here, there's many forms that 2 pi can take. If we start with 2 pi over 1, we could turn it into 4 pi over 2. We could turn it into 6 pi over 3, 8 pi over 4, 10 pi over 10 pi over 5, and so on. So whatever we need to do to get those denominators the same, the number on the top is essentially twice whatever the value is on the bottom. All right, and then our second learning target here was to evaluate trig expressions for angles in radians. All right, and this is using our unit circle. So to find cosine of a unit circle angle, sine of theta, or tan of theta, we're going to use our unit circle to find the x and y values. And remember that sine is the y value of the coordinate, cosine is the x value, tan is the y value over the x value. I did want to say something quick here about problem number 1, part A, where it's having us sketch the angle. So the first angle that is given to us there is 7 pi over 8. And we haven't done anything with a denominator of 8. That's not an angle that is officially on our unit circle. But I want to show you here that we can still think about sketching the general position of that. Thinking about the top half of our circle that we know is equal to pi radians. Well, if we want to think about a denominator of 8 here, we would have to have 8 equally sized sections. So if we divide do the same thing over here in the second quadrant, these lines would not line up with our unit circle lines. They would be a little bit off, but it gets us to that denominator of 8. And so one of these lines is going to be 1/8 of the way to get to pi, and so it would be pi over 8. And so if we keep counting upward, we see that 7 pi over 8 is going to be this label over here on the left. It's like the last little line right before we get to pi. So I wanted to give you a little guidance on that one. The other angle that it's having you draw should be familiar. It is one that's on the unit circle. So let's take a few minutes here to try out the rest of those questions in the check for understanding. All right, so we're going to come back together and take a look at these. So we talked about sketching the 7 pi over 8. The 5 pi over 3 was actually the same that we did in our activity. So that terminal side ended up being right about here. That one is one that we label on our unit circle. Just going to go ahead and show 7 pi over 8 would be right about there. So anytime we're finding a coterminal angle, this is where we're going to add or subtract 2 pi. And the version of 2 pi that we use is going to depend on what our original denominator is. So in this case, for the 7 pi over 8, I'm going to add 16 pi over 8. So notice how that 16 pi over 8 is really the same as 2 pi over 1. I just multiplied the top and bottom by 8 so that the denominators could be the same. When we add across the top, we get 23 pi. We're going to keep our denominator the same. We did 5 pi over 3 in the activity. So to get a coterminal angle there, we could add 6 pi over 3, which is another version of 2 pi. And that's going to turn it into 11 pi over 3. I added 2 pi on both of these. You also could have subtracted 2 pi, and that would be another correctly way to answer this question. Let's talk about the ones here now at the bottom. So here we wanted to draw the angle. So this is getting us a little bit more practice with the way that our angles are labeled in radians. So first I just drew 3 pi over 4. And then we want to get, in this case, it's asking us for the sine. Well, the sine is equal to the y value. So this answer here would be square root 2 over 2. Now for the last one here, cosine of 11 pi over 6. Cosine is equal to the x value. So when we're taking a look at our labels on our unit circle, I can see here that the x value is root 3 over 2. And that's what we're doing for a cosine. If it would have asked us to find tan, that's going to be the y value over the x value.
Later.